Hi, and welcome to today's video. Today we're going to be answering 3 questions. And well, all 3 have to do with threading on the lathe. Now, we already have several videos that look at threading on the lathe, and I'll be putting up links to those videos as this video progresses. But they will also all be with clickable thumbnail links at the end of this video. So let's get to it. The first question is going to be about the thread chasing dial and how do we use it. So we'll be looking at the divisions and what those divisions mean. The next question, well, is a bit intertwined with that, because the next question is, can I cut a thread if I don't have a thread chasing dial on my lathe? The answer to that question is yes, definitely. But you're going to have to be careful about how you go about it. And well, the third question has to do with non-standard threads. And that may seem a little bizarre, because a standard thread, well, is something that you're going to want to measure, and most people think that if you're producing a non-standard thread, well, there's no reason to measure it, you're just going to make it to whatever you feel like. It's a whimsical thing. But it isn't, because you may want to reproduce that thread, that non-standard thread, somewhere down the line because the part is worn or whatnot. And well, how can you ensure that the thread that you're going to produce at a later date is going to conform to the thread that you've produced today? Now, when we thread on the lathe and we're going to be measuring a thread, well, we use the 3-wire method. Now, we could use an optical comparator. We could use a go and no-go gauge. Yes, that's all possible, but as a general rule in the shop, a home shop at least, we're going to be using the 3-wire method. Now, if you're going to be using the 3-wire method, well, you have to get your form perfect to start with. And what does that mean? Well, you're going to have the proper V. And you're going to have that V perpendicular to the axis of rotation of the part that you're threading. And you're going to have the proper pitch, the pitch that you've chosen for your non-standard thread. But what are we going to be doing about the outside diameter of the thread and about the measurement over the wires? Because it's not the crest nor the root of a thread that comes in contact. We've seen this in some other videos, and here's a link to one that specifically talks about that problem. Now, threads contact on their flanks, and well, to measure the position of the flank of a thread, an external thread, we do that by 3-wire measurement. And to do that, we need numbers, but a non-standard thread won't appear in the machinery's handbook. So how are we going to get those numbers, that pitch diameter that we need, that wire diameter that we need to measure the non-standard thread that I'm cutting? And we'll be taking a look at that at the end of this video. Now, if we have any hope of understanding how to use a thread chasing dial, well, we're going to start by going to take a look at what a thread chasing dial is used for. So let's head over to my little lathe here, and it's right next to me here. That's why I'm looking in that direction, and we'll take a look at what a thread chasing dial is used for. Now, the term thread chasing dial kind of says it all. It's a dial that indicates to me the proper time to engage the split nut onto the lead screw to ensure that my cutting tool comes back to the same groove, because it's a thread. There's one groove for a single start thread of constant section, usually a V, and in most cases a 60-degree V, on the outside diameter of a part. Fine, so that's what it's used for, but why do we need it? Well, because we're going to be cutting a thread with several passes, and we're going to be doing that, well, because it's difficult to cut a thread in one pass unless it's a very, very fine thread. Now the thread chasing dial, well, is mounted usually on the side of the apron. And, well, it has a gear that's connected to a shaft that's connected to a head that has a line or a graduated line on it. Sometimes have several. Now this one here only has one, and we'll see why, but this is one that I've made for myself because there was none on this dumpster dive of a lathe that I picked up years and years ago. So that's the basic thing, and we see that the gear meshes with the lead screw, and it's going to give me an indication of the relation between the lead screw and the position of my tool. So let's take a look at that. You're going to want to engage the split nuts just as the two lines match up. And unless I change the gear setup, either the gearbox or the reverse gear setup, well, I can engage on that line, and the relation between the saddle's longitudinal movement and the spindle's rotation will remain the same. So it's pretty easy to see how that thread chasing dial helps me to know at what precise moment that I need to engage the split nuts so that my tool falls back into its groove. Now there's sequences, and it's important to follow the proper method for cutting a thread, because Lord knows it is possible to get the tool to go out of its own groove even if I use that thread chasing dial. But if I follow all the proper procedures as we've seen in our cutting a thread on the lathe video, well, all should be well. But there is a second reason for using a thread chasing dial, and that is to save time. Now, this lathe I found at a scrapyard many years ago when I was young and poor and couldn't afford to do things like order the proper thread chasing dial. So at that time, well, I made myself this thread chasing dial, and I never upgraded because I had no reason to. Why? Well, this is a home shop and I'm in no rush. But if I wanted to save time, well, I'd have a thread chasing dial that had several lines on it and not just one as I've produced here. And that, well, would save me time because it would indicate to me alternate moments where I could engage, where I wouldn't have to wait for the thread chasing dial come all the way around before re-engaging for a second, a third, or fourth path. So how does that work? How do I read those different graduations? Well, let's head over to the whiteboard and take a look. So as we've just seen, my thread chasing dial has only one indicating division on it. That's because I made it myself and, well, I'm lazy. But this is the basic layout for manufactured, or the thread chasing dial that should have come with my machine and that is on most machines. So 8 divisions, 2 different ways of representing it. Here I have 8 divisions that are divided into main divisions, the ones that are numbered, and intermediate divisions that aren't. But at the end of the day, I have 8 equally spaced divisions. The more modern way of doing it would be to have 8 divisions, but numbered 1 to 8. So, what do these divisions mean, and how do I use them? Here are my 2 layouts. I think it's important to note that these are imperial thread chasing dials. So, imperial threads, I can have different number of threads per inch. I could have 20, 13, or even fractional number of threads per inch. In this case, I have a quarter 20. An even number of threads per inch can use any of the 8 divisions on the dial. That's true for here and for here. Even number of threads per inch. Uneven number of threads per inch can use any of the main divisions. So 1, 2, 3, and 4. In this case here, it would be 1, 3, 5, and 7. Uneven number of threads. If I have a fractional number of threads and it's expressed in halves, well, I could use any opposing main divisions. So 1 and 3 or 2 and 4. Not and, or. So if I start on 2, I can continue either on 2 or on 4, but not on anything else. If I start on 3, I could continue on 3 or on 1, but not anything else. And if I have a fractional number of threads per inch that is in a fraction expressed other than a half, well, you're stuck with using the exact same division for each pass. So if you start on 1.5 here, you're going to have to stick to 1.5. Same thing in this case. So even number of threads, any of the divisions will do. Uneven numbers, well, we'll have one of the main divisions, and any one of those main 4 divisions can do. Fractional in halves, opposing main divisions, 1, 3, 2, and 4. And fractional in anything other than halves, I'm stuck with whatever division I start out with. So in this case, basically the same. Even number, any of the 8, sorry. Uneven number, 1, 3, 5, and 7. And fractional in halves, 1 and 5, 3 and 7. Fractional in any other thing than halves, I'm going to be stuck on one of those main divisions. It's really just that simple. If I'm cutting a thread normally, let's say an imperial thread, I'm going to cut, stop, pull out, come back to the start, somewhere past the start of the thread, plunge back in, check my thread chasing dial for a second pass, and engage and take my second cut. So let's say I have a shoulder and I have a threading groove at the end of the thread to separate the thread from the shoulder, and that's a normal way of doing things. Well, what would I do? I'd take a cut, and before the tool crunches into the shoulder, because we don't want that to happen, well, I would disengage the split nut. So I'd be very concentrated, I'd cut, and bang, I'd just disengage them when I get into that groove, the clearance groove. And I pull out, come back to the start, plunge back in, check my thread chasing dial, and start over again. Stopping on a dime, that's one thing that the thread chasing dial gives us. Now, let's say we were cutting a left-hand thread, and that means that in the normal direction of rotation of the part, I would be feeding from the headstock to the tailstock, and that would give me a left-hand thread. If I were doing that, and there was nothing in the way, well, my tool could easily run off the end of the part. And because of that, because there's no danger of running into something, I could just turn the machine off and let it wind down, never disengaging the split nuts. If I never disengage them, well, I don't need a thread chasing dial, because it's used to re-engage in the proper position. And in this case, I wouldn't need to. So what would I do? Well, I'd take a cut, turn the machine off, let the machine wind down as it continues to advance, back the tool off so that it won't hit anything on its return movement, put the machine in reverse, okay? So change the direction of rotation, and that will feed you back towards the start of the thread. Now, obviously you don't want to hit anything, so you be careful that you turn off so that you can wind down and end up where you want to be to start your next cut. Feed into the part and just turn the machine on again. It's going to fall into the same groove because you've never disengaged the split nuts. But be careful. When I say reverse the machine, you have to remember that there's two different ways of reversing a machine. The first way would be to reverse it electrically. And for that, well, you need a switch that's reversible. So you can go in the normal direction of rotation, or once it's wound down and stopped, you can go in the reverse direction. The next would be to introduce an extra gear in the feed's drivetrain. And for that, well, we could do something like this here. Just add in an extra gear. But be careful, that reverses the direction of feed, but it will not reverse the direction of rotation of the part. And, well, there's another problem with this. Should you choose to reverse the direction of feed by using the electrical switch without disengaging anything, well, that'd be a good choice. It is the way to go about it, because you're not changing the relation of any of the components here. However, should you use a reverse gear in the head by adding or taking away, you're going to get in trouble. The chances of things falling back in its proper groove are about nil. Why? Because when you disengage one gear and engage the other, well, you're changing the relation between the lead screw, the saddle, and the part's rotation. And as I said, unless you're incredibly lucky, it will never line up. So that's really not very complicated. If we wanted to do the same explanation in metric, well, it would be quite similar. The only difference is the divisions on the dial would be different, because a metric thread chasing dial isn't the same as far as divisions go as an imperial thread chasing dial. But the principle is the same, so we won't be getting into that explanation. And, well, we also answered the question, can we cut a thread without a thread chasing dial? Yes, as long as, and we saw that before, as long as we don't disconnect the split nuts. Now, if we don't disconnect the split nuts and we're threading up to a shoulder, we have to be very careful. We want to be able to retract that tool very quickly, and we want to be able to stop the machine very quickly. So we need a good brake and some kind of mechanism to pull that tool out of there very quickly. If we don't have either of those, avoid doing it. It is a little on the dangerous side. Okay, so we can cut a thread even if we don't have a thread chasing dial. Great. Last question had to do with, how do I figure out, how do I get numbers for a non-standard thread? And well, you can calculate it from scratch, and that is quite involved. I mean, just check out the formulas in the Machinery's Handbook. You'll see that it gets confusing after a while. But threads are linear. What I mean by that is the formulas used to calculate everything on a thread isn't squared or cubed or whatnot. It is to the power of 1, and that means that it's a linear thing. They are linear equations, and that means that things are proportional. So we can fudge things. Now, we won't be exactly to a 10,000th of an inch on the right dimension, but between you and me in a home shop, we can forget about the 10,000ths of an inch, and especially just one. And that's going to be the kind of error that you'll end up with if you fudge things. And we can fudge it because it's proportional. So let's say I have a 1/2 inch 13 thread, and that's standard. And I have a non-standard 3/4 13 thread. Well, I can use the dimensions of the 1/2 inch 13 to figure out the dimensions of the 3/4 13, because they have the same number of threads per inch, and well, they are in relation in a linear fashion. So we'll take a look at that in a second. Why are we getting these numbers? Well, if you're going to be cutting a non-standard thread, you may well want to reproduce it further down the line. And I mean, you're going to want numbers also to know where you're going when you're cutting, when to stop, when am I at the proper depth. And for that, well, we're going to use the 3-wire method of measuring a thread, because in your home shop, that's really the most accurate way of going about it. And to do that, well, we need numbers. Now, we need the outside diameter of non-standard thread because you got to produce the part, and we know that the OD, outside diameter of a thread, is never equal to its nominal diameter. So a 3/4 diameter thread does not measure 3/4 of an inch. It's a little less for the outside diameter. And we're also going to want to know, well, the number of threads per inch, and that's a given. And we're also going to want to know the pitch diameter, and well, we'll have to figure that one out. And we're going to want to know the wire diameter. And seen as for any given number of threads per inch, the V doesn't change, so a 1/2 inch 13 and a 3/4 13 thread has exactly the same depth and width of thread, V. Well, that means that we can use the same wire that we use for a 1/2 inch 13 on the 3/4 13. All we have to do is calculate what the measurement will be over the wires. And well, for that, as I said, we need the pitch diameter. So let's head over to the whiteboard and take a look at those numbers. So I have here two different threads that are very different. 1/2 inch 13, 3/4 13. They have the same number of threads per inch, but their nominal diameter is quite different. Actually, this is a 1/4 inch larger. But they are different for another reason, in that this thread exists. I can find it in the handbook with the numbers that I need to calculate my measurement over the wires, and this one doesn't exist. I can't find any numbers on this one in the machinery's handbook. And this is the one that I want to produce. Why? No reason. I'm not really going to produce it. It's make-believe. But it is a thread that doesn't exist. So we'll take that as our example. Now, this 1/2 inch 13, as I said, it exists, and I can get numbers. OD, outside diameter, situated somewhere between 498 and 487. That's the major diameter or the outside diameter, depending where you hail from. Pitch diameter, that's the diameter at the center point height-wise of the thread, and I have somewhere between 448 thou and 443 thou. And down here I have wire diameter, because I'm doing this to get numbers that I can use for my measurement over the wires. Well, largest wire possible, smallest wire possible. So largest is 69 thou, smallest is 43, and the pitch line contact, the wire that will give me the most accurate result, well, is 44 thousandths of an inch in diameter, and it's a 3-wire method, so I'm going to need 3 of those. Whichever one I choose or I have is the one that I'm going to use in the formulas to calculate the measurement over the wires. Now, what I need to produce the thread is a blank to start with, so the OD. And what I did here, and it is really the simplest way of going about it, is I took the difference between the two nominal diameters, which is 250 thou, and I add 250 to the numbers I have here. And that gives me an OD of 748 to 737, a pitch diameter from 698 to 693, and a wire diameter that's going to be the same, because 13 threads per inch has the same size of V. So the V for both of these threads is the same size, so it's going to be the same wire. Now, I've calculated this 3 different ways just to make certain that I wasn't leading you down a path that led to heartache. No, this works. So I always get within a 10,000ths of an inch the numbers that I have here. So this simplified way is, if that's a non-existing thread and it has a pitch that I can find somewhere else in the handbook, like 1/2 inch 13, I use the numbers for the thread that does exist plus the diameter difference, and I end up quite accurately, as I said, within a 10,000th of an inch to something that I can use. For my metric friends, the same logic applies. You're going to use a thread that has the same pitch, and when you calculate over the wires, whether it's metric or imperial, it works out to about the same thing. It's really the same formulas because they're all based on a 60-degree V, and as we know, degrees, 60 degrees, well, are the same in metric and in imperial. Now, I'm not going to do an example of the 3-wire method. It's long and drawn out, and this video has been long enough. But I do have some examples of that, and you can go and check out the threading on the lathe video where I do an example and I explain the 3-wire method for measuring threads accurately. That concludes today's video. I hope that it answers the questions of the people that asked me those questions, and maybe for the people that didn't ask them as well. Until we meet again, have fun. Be safe. It's so important. And happy machining.